Okay, so we're starting chapter 13 here. 13.1, we're dealing with vector functions and space curves. And this is actually the first time we're actually going to do any calculus in this class. It might seem a little bit odd. We've gone through an entire chapter of the book in what's supposedly a calculus course, but we've done no calculus yet. And that's because we're setting the stage for a lot of stuff that's going to come up in later chapters. But here we're going to be looking at limits, derivatives, and in this section it's actually just limits and continuity as far as the calculus is concerned. In 13.2 we're going to look at derivatives and integrals of these things called vector functions. But the goal here is actually not so much on the calculus part of it as it is understanding what a vector function is and how it leads to these things that we call space curves. So let's start with some definitions. A vector function is a function that takes a scalar or a real number as an input and produces a vector as an output. That vector can be a vector in R2, it can be a vector in R3, it can be a vector in Rn for that matter, but we're going to focus primarily on vector functions that have outputs in R3 or in 3 space. So for that purpose, I have an example of a vector function down here. The function is usually going to be labeled with an R. Notice that it's bold, indicating that it represents a vector. R of t. T is the input, which is a scalar. And in this case, if it's a vector function with outputs in R3, the vector function might look something like this. Notice we have a vector with 3 components, but each component is a function of t. F of t, g of t, h of t. And we understand these functions to just be real valued functions. We'll look at an example in a moment. Alternatively, I could write it in this form as well, using the standard basis vectors I, j, and k. It's very common for us to do this in place of this. Either of these, though, but will represent a vector function. These individual functions here, f, g, and t, we call component functions because they are where we get the components of that vector. So, one thing I also want to mention before looking at an example is something that I don't think the book actually emphasizes quite yet in this chapter, but it's something that's a common notation in math classes beyond this one, which is a type of function notation that indicates what the domain and codomain of a function is. So if R is a vector function that takes inputs that are scalars, those scalars belong to the real numbers, and the set of real numbers we denote by this capital R here. The outputs for this particular function all live in R3. So this notation, R with the colon, and then this R, the arrow pointing towards R3, is showing you where the inputs and the outputs live. The inputs, again, are real numbers, and we'll actually see that the domain doesn't have to be all real numbers. Sometimes there's restrictions on the domain. We'll see that in the next example. The outputs live in R3, but not necessarily every vector in R3 can be an output of a given vector function. So rather than call R3 the range, which would be the set of all outputs, we call it the codomain, which is a set that contains the range. That's a discussion that's not terribly important for this class. You don't really need to know what the term codomain is. You don't really even need to know this notation, but it kind of helps to at least have seen this notation for some of the stuff we do later. So moving on, the first example we want to look at is finding the domain of a vector function. R of t equals square root of 9 minus t squared. That's our first component function. Sine of t, that's our second component function. 1 over t, that's the third. So basically, in order for a scalar t to be in the domain of this function, it needs to be something that belongs to the domain of all 3 component functions simultaneously. And what's helpful here is to just look at the domains of each individual component function and then take the intersection of those. So determine what parts of each domain do all 3 functions have in common. So what is the domain, for example, of f of t equals root 9 minus t squared? I'm going to find that on its own. I'm not going to go through the process of doing this. This is more of an algebra thing, but it's fairly easy to see that this would be the closed interval from -3 to +3. If I were to graph this in the plane, it would look like a semicircle of radius 3 centered at the origin, the upper semicircle. This is where the domain would have to be in that case. What is the domain of that second component function? Sine of t. Well, we know that that would be all real numbers. Okay? Finally, what is the domain of that last component function? We could call that h of t equals 1 over t. What would the domain be there? The only thing that does not belong to the domain of this function is 0. So I could say that it's a union of these two intervals here. Okay? This is notation you should have seen before, this union notation. It just means that the domain consists of both of these intervals together in one set. Really the only thing left out of this is the number 0. What I want to look at is the intersection of these three domains here. And basically what that means is what real numbers belong to all three of them simultaneously. Well, notice anything outside of the interval -3 to 3 we can just forget about, because then we wouldn't have any of those numbers in the domain of f. And then in addition to that, notice the second component function doesn't put any restrictions on the domain. You can plug anything you want into a sine function, so there's nothing really to consider here. However, if we already know our focus has been narrowed to this closed interval from -3 to +3, does h of t conflict with this in any way? Or does the domain of h of t conflict? And it does, because this interval contains 0, but this domain does not. So we have to remove 0 from this interval. That means the domain of R is this closed interval with the number 0 removed. One way of writing that is like this. Union of two intervals, and we call these half-open intervals because they're open here but closed here. Okay, so that would be the domain of that vector function. Anything within either of these two intervals that are making up this union can be plugged into this. Okay, so that's a simple, find the domain type of question. Next up, let's talk about limits. So taking limits of vector functions is really as simple as just taking limits of each of their component functions. That's how we define a limit. So again, remember the input of a vector function is a scalar. And so when we talk about limits, we can talk about limits as that scalar approaches some specific real number. In this case, if I mention the limit as t approaches some number a of the function r of t, we define that to mean the limit as t approaches a of each one of these component functions inside that vector. Okay, provided the limits exist in all three cases at the same time. So here's an example, very straightforward example. I want to find the limit as t approaches 3 of r of t, where r of t is this vector function. Notice we're using that ijk notation here. So first I need to determine what are the three component functions, and then after that, what are the limits of those? So the first one, the limit as t approaches 3 of t squared minus 9 over t minus 3. That's the first component function in this vector function. And this is a classic, type of problem when we're first introducing limits in Calculus 1. There's different ways to solve this. You could use L'Hopital's rule, but that's almost overkill here. You notice if you factor the numerator here, you get t minus 3, t plus 3, and then you get some cancellation there. So I get the limit as t approaches 3 of t plus 3 as a result. That gives me 6 for that component function. Then if I look at the next component, limit as t approaches 3, what is the second component function? Well, this minus j here, remember, if you don't see anything in front of that j, you can imagine there being a 1 there. So really it's -1 that we're looking at. And we know that the limit as t approaches anything for a constant function is literally just that same constant. Okay, finally, let's take a look at this guy. This is the limit as t approaches 3 of sine of t minus 3 over t minus 3. There's different ways you could approach this one. If you notice, if I substituted 3 into both the numerator and the denominator here, I get a 0 over 0 indeterminate form. So you could use, L'Hopital's rule. That's a totally valid way of doing it. In Calculus 1, again, when you're first talking about limits, you talk about the limit as t approaches 0 of sine of t over t, and you show that that's equal to 1. With a simple variable substitution, we could accomplish the same thing here. In any event, no matter how you approach it, the limit here is going to equal 1. And so that tells me that the limit that we're looking for up here, the limit as t approaches 3 of r of t, is 6I minus j plus k. Remember, the negative 1 is the coefficient here, the positive 1 is the coefficient here. Alternatively, I could have written that as 6, negative 1, 1 in that angle bracket notation. That would have worked also. Either of these are fine. Okay? Notice in this case also, our answer is a specific vector because we're talking about a limit. So we're not getting another function out of this. We're getting, real numbers for our components. All right. Continuity is a natural thing to talk about after talking about limits, and we define continuity of a vector function or a continuous vector function in the same way that we define it for real valued functions in Calculus 1. So in Calculus 1, typically when you're introducing continuous functions, you're given an intuitive idea of what a continuous function is. You're taught that a continuous function on some interval or at some value, at some specific number, is basically the same thing as saying that you can draw the graph of that function without picking up your pencil. There's no jumps or breaks or holes in the graph, essentially. But again, that's just an intuitive definition of continuity. It's not a rigorous definition, which means for mathematical purposes, it's usually not enough. And then you're taught that a continuous function, more formally speaking, can be defined this way. If we say that a function, in this case r of t, a vector function, is continuous at a specific real number a, so at just a single point, what that means is that the limit as t approaches a of that function not only exists, but is also equal to r of a. In other words, the limit is the same thing that I would have gotten by plugging a directly in to that vector function. Now, again, Calculus 1, you spend a lot of time looking at properties of continuous functions and exploring that concept, which we aren't really going to do here because a lot of the same ideas carry straight over into the case of a vector function. As we're about to see, vector functions determine these things called space curves, and if a vector function is continuous, then that kind of means the same thing. It means that space curve can be drawn or graphed without any breaks or holes or jumps of any kind. So we're just kind of going to give this a passing mention so you know what continuous means in the context of vector functions. Okay, so again, like I said at the beginning of this video, we're focusing primarily on vector functions in R3, not exclusively, but primarily, which means vector functions whose outputs are three-dimensional vectors. They have 3 components in them. Now, in Chapter 12, we spent a lot of time exploring 3-space. In particular, we looked at graphs of equations in 3-space, and we saw that they typically give us these surfaces, whether it's a plane or a cylinder of some type or a quadric surface or something else entirely. Graphs of equations in 3 variables tend to give us surfaces. But it's not a big stretch of the imagination to see that we can also graph things in 3-space that aren't surfaces. In particular, we can graph curves, sets of points that go together to create a curve. And those curves generally don't arise as an equation in 3 variables the way a surface does. These space curves, which we call them because they are in 3-dimensional space, arise as the graph of a vector function instead. So vector functions lead us to these space curves, but specifically, how is that? How do they do that? If the output is a vector, then how do we end up with a set of points in space instead of a set of vectors in space? And the way that we do that is as follows. So let's suppose we have a vector function some general vector function here, r of t equals f of t I plus g of t j plus h of t k. And for this section here, we're going to assume that we're talking about a continuous vector function so that we get these curves with no breaks in them. What we're going to do is interpret the outputs of this function. So for anything that we plug in for t, we get a vector in R3, but we're going to interpret those outputs as position vectors. Remember, whatever vector we get from plugging a number in for t here can technically be thought of as being anywhere in space, but if we specifically require them to be thought of as position vectors, that places their initial point on the origin here. It also means that the terminal point of that vector, whatever its components are, those will exactly match the coordinates of the point that coincides with that terminal point of that vector. And so in this sense, if we take the output vector from our r of t function and interpret those outputs as coordinates of a point instead of components of a vector, that's what gives us a space curve. So you can see in this graph here we have some r of t, and here's its component functions, and of course the output is a vector. That's this blue vector here. But that blue vector is going to have a terminal point, which in this case is called p, which coincides with a point on the curve. So we kind of think of, if you let t vary, the vector that's going to be changing as t changes is essentially tracing out a space curve with its terminal point. That's how you want to imagine that. And there's our connection between these vector functions and space curves. Okay, so let's kind of get used to working with those space curves now. I wanted to mention here as well, even though our focus is primarily in R2, the exact same stuff that we've been talking about in the context of space curves can be applied to plane curves as well, which are curves in R2. So, the only difference is that the vector functions are only going to have 2 component functions in those cases instead of 3. Okay? All right. So here's an example, and you can see I've already gotten the graph printed on these notes because it's very hard for me to draw that well. I'm just going to kind of walk you through this. In this case, we're asked to graph a vector function. R of t equals 4 cosine of t, 4 sine of t, and then the third component is just a t by itself. For working with vector functions and space curves, it's really, really critical that you are comfortable with parametrizing curves. Something that you spend time doing in Calculus 2, which, you look at derivatives and integrals of parametric curves, but you even talk about it earlier than that. Pre-calculus, you talk about how to parametrize a curve. It's critically important that you know some of the basic parametrizations for curves in the plane. So if you look at this vector function right here, 4 cosine of t, 4 sine of t. Ignore the t at the end just for a second. If I think of this as x and y, and I want to look at the parametrization or the curve that parametrizes, this is a circle of radius 4. Okay, so that would be -4 right there, 4, -4, 4. And right here, that corresponds to when t equals 0. If you plug t equals 0 into these first 2 components here, you're going to get 4, 0, which is this point. And then as t increases from 0, the curve is going to, or the point that we get traverses this circle in a counterclockwise fashion. So that's the reasoning for that. I'm not going to go into because, again, this is old news for us, but these 2 components parametrize that circle. Okay, now what I want to do is try and see how that 2-dimensional case where I ignored this third component relates to the 3-dimensional case where this last component is a t. So again, the x and y coordinates of any point that comes from this vector function will have to lie on this circle in the xy plane. But adding this t here is only going to change the z coordinate of these points. So essentially what that does, you'll notice in this graph right here, there is a point at the origin, or sorry, it's not at the origin, that's kind of below it. There's a point here on the x-axis with an x-intercept of 4. Okay, so you notice the way that this graph has been rotated. The x-axis is here, the y-axis is here. We have this point right here, and this would correspond to when t equals 0. Now, we know that the x and y coordinates will kind of move around this circle counterclockwise, and in this graph, counterclockwise is going to look like this, right? But as t increases, the z-coordinate of that point is also increasing, so it's not going to just stay in the xy plane going through the circle. That increasing of the z-coordinate is going to lift that point vertically as it rotates counterclockwise, creating this curve that we call a helix. A helix should be a familiar term, a familiar curve to you. A double helix, where you have two of these together, is the shape of a DNA. You know, everybody's seen kind of the model of DNA. It's very similar to this, but with a double helix. Okay, so notice how we had to kind of think through what this curve would look like. We started by looking at just 2 of the 3 components here and noticed a familiar parametrization from those, looked at it in just the plane, and then saw what happens when I include this 3rd component here. It kind of takes that point, and as it's doing this, moving along this parametrization, also pulls it in whichever direction, in this case the z direction. One thing that's also worth considering is what would happen if I swapped this t with one of these first 2 components. For example, what if I looked at 4 cosine of t as my x component still? T is maybe moved here, and then 4 sine of t is moved here. Well, the 4 cosine of t in my x component and the 4 sine of t, which would end up in my z component if I juggled these 2, would still go together to make a parametrization for a circle, but that circle would now be in the xz plane. Here's the x and z axes. You can picture the xz plane here. The t being in the y direction, or in the y component, would pull that point as it circles around that circle of radius 4 in the xz plane. It would pull it along the y-axis, so that would cause this helix to be oriented around the y-axis instead of the z-axis like it currently is. Okay, I think that's where I'm going to end this first video. We just have a couple more examples to look through. 13.1 is not a terribly long section, and we'll wrap that up in the next video.